Mm. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. Okay, so today is second lecture of week 11. These blinds get worse and worse every day, so I'm gonna be like kind of like hiding from the sun until the sun sets. Okay, so the plan for today. So I did post the final project specifications, and so I did want to talk about that. And so we'll do that for the first maybe 15, 20, 30 minutes of class. And then we'll go ahead and continue on with the next algorithm that we're going to discuss, which is pattern search. Okay. So we just about finished coordinate search last time. We didn't quite get to talking about the code, so I'm going to start with that, and then we'll talk about pattern search for the rest of today. Okay. Okay. So homework 5 is out there. So I know some of you have already gotten started on it, so that's good. I've gotten some questions on problem 2B, which is the problem on random walk. And so that one was actually kind of a challenging one because because of the randomness of the algorithm, and the objective function that I gave you actually has a lot of local minima as well. And so probably what you're going to find is that the results are not going to be quite like what I have on the homework sheet. And in fact, what you might find is that the objective function that you're getting is probably going to be in the order of 10 to the 6th as opposed to 10 to the 8th. And so that was a little bit of a typo on my part, so I need to go in and correct that. But you should get something around the order of 10 to the 6th. There was just kind of a small typo in my code in terms of how I decreased the step size. So I'm going to go ahead and correct that after the class today. But you should, if all things kind of work well for the random walk, you should get an objective function value around 10 to the 6th. Okay. Okay, so I think that's it for my announcements. Are there any questions I can answer before we get started for today? Okay, all right. So let's talk about the final project. And so I just posted it today. Let's see this one. Okay, so this is the document that you'll see on the Canvas site. So this is the instructions for the final project. Okay. So first of all, I think probably the question on everyone's mind is when is it due, right? So when I give final projects in my class, I like to have them due the Monday after finals week, just to give you guys a little bit of extra time, because I know you guys can be really busy during that week. And so the due date for the project is going to be Monday, December 18th, by 11:59 p.m. And that's about as far back as I can push it, because I do need to finish grading everything before Christmas. And that's this class as well as my 2 other courses that have final projects. So that's about as far back as I can push it. Okay. Okay. So the idea behind the final project is to use optimization, and we're actually going to be using it for an engineering problem here. So we're going to be using optimization to design a truss. And so what you have here is a 25 bar truss, and so it's a truss structure with 25 elements in it. Okay. And there is about 10 nodes, right? Yeah, 10 nodes in the system. Okay. And we're going to be optimizing the design of this truss based on kind of some criteria that I'm going to give you in the problem and in the specifications. Okay. So this is the ultimate goal. And so I would this is definitely a much more difficult optimization problem than anything that we've seen in the class so far. And so to reach this point, I've given you kind of an easier problem to work on as well. Okay. And so this is the easier problem. So this is the 10 bar truss. It's only a 2-dimensional problem. And this one only has 4 design variables. So there's only 4 design variables in this problem, whereas for the 25 bar truss there are 10 design variables. Okay. So this truss here, the 10 bar truss, this is a little bit more consistent with kind of the problems that you're considering in homework 5. In fact, I think one of the problems I gave you in homework 5 does have 4 design variables. So this is pretty consistent with that. Okay. And so basically the idea is we're going to use optimization to choose the dimensions for this truss, and so the lengths here, as well as its cross-sectional area, as well as its Young's modulus. Okay, so we're going to be optimizing basically every aspect of this truss. What we want to do is we want to try to basically minimize the cost of construction as much as possible, while also making sure that the truss doesn't break. Okay. And so you're basically going to make basically the cheapest design as you can, you know, while still satisfying its structural requirements. Okay, and each of these problems will have its own constraints as well that you need to take into consideration as well. Okay, and so it's really, you know, it's really just meant to be just an application of everything that we've been learning so far, except that, you know, we're actually working on a physical problem more so than just math problems, because, you know, all the other objective functions that I've been used so far has just been math. Okay. Okay, so let's talk a bit more about the specifics. And so, you know, for each of these trusses, and so you're going to be required to solve both of these trusses here. I want you to solve them each with two different optimization algorithms. Okay, and so, you know, kind of, you know, we've been doing this for the past week and a half or so, and we're going to continue doing this until the end of class or the end of the semester. We're basically going to be going over different algorithms for solving these types of problems. Okay, where each algorithm kind of has its own strengths and weaknesses. So I want you to basically solve the same problem twice with two different algorithms. Okay, so overall you should have 4 codes, and so you should have, there's 2 trusses, and you need to write 2 codes per truss. And so that's 4 codes overall. You can reuse the same algorithms. In fact, I encourage you to do so. And so whatever algorithms that you choose for the simple problem, you can use those same algorithms for the more complicated problem as well. But of course, you're going to have to make changes in the code to account for the fact that it's a much bigger problem. Okay. And so even though this says you have to write 4 codes overall, you know, these algorithms are going to be very heavily inspired by the examples we're doing in class. And so my idea is that, you know, you're not writing a whole algorithm from scratch. You're basically just kind of repurposing some of the examples that we're using, and just having it fit towards this problem. Okay. So, you know, even though it sounds like a lot of code, you know, my hope is that it's not going to be a ton of code that you have to write, because you can just kind of reuse a lot of the code that we've been going over in the class. Okay. Okay. So let's go over the specific problems. So for the 2D truss, the 10-bar truss, I've already talked about the 4 design variables that you're going to be working with, right? So one is the length, the horizontal length of the truss. Okay, so that's given by this variable L. We have the vertical height of the truss. Okay, so that's this variable H right here. We have the Young's modulus, and so that is basically a material property of the truss itself. Okay, as well as the cross-sectional area. And so the cross-sectional area, it's not shown here just because these are slender bars, but that is something that you need to specify for these kinds of problems. Okay. Okay. And so if you look at the way that this truss is loaded, we have 2 vertical loads here. So we have a vertical load on node 4 and a vertical load on node 2, right? And so as a result of those 2 loads, and as a result of kind of this structure being made of trusses, you're going to see the truss kind of deform in this way. Okay, so this is the kind of the nice thing about this code. So I was fortunate enough to find a code to kind of help me with the visualization of these truss structures. And so, you know, from this code, you'll be able to see how the truss is going to deform, which is kind of, you know, not very much unlike what you would see in like an ANSYS or a finite element software. Okay, and so I wanted this to be a big part of the project, because I want you guys to kind of visualize, you know, kind of the result of your optimization in terms of what effect that's having on the structure. Okay, because it's one thing to kind of, you know, work through an algorithm and get the numerical value for the design variables, but, you know, eventually those design variables are going to be put in practice. So I wanted you guys to kind of see what effect that would have. Okay, and of course this figure here is going to update based on the optimal value that you get for L and H as well. Okay, and so if you get a small value for H, and so, you know, then the figure is going to be reflected accordingly, and so it's going to be kind of a shorter thing. And if you get a smaller value for L, then it's going to be shortened as well. So the geometry actually does reflect, you know, the changes that you're making through the optimization, you know, which I thought was pretty cool. Okay. Okay, so let's talk constraints, right? So both of these problems are going to be constrained optimization, and so you're going to need to implement the constraints in some way. Okay. And so for the simple truss, we have 3 main constraints. And so the first constraint is on the total horizontal length of the structure. And what we say is that the total horizontal length cannot be less than 500 inches. Okay. And so the total length has to be at least 500. It could be longer, but it has to be at least 500 inches. Okay. The ratio of the height and the total horizontal length of the structure cannot exceed 0.2. Okay. Or excuse me, cannot be less than 0.2. And so, you know, you have to have at least a decent amount of height there, right? Again, this is an inequality constraint. And then constraint number 3 is one that has to do with the structural integrity of the structure. So one thing that the code will give you is that it'll compute the amount of force that each truss member is experiencing. And so based on your design, the maximum force experienced by any member in the truss cannot exceed 350,000 pounds. Okay. So those are the 3 constraints you have to adhere to. And so whatever optimal design that you get from your code, it has to satisfy these 3 constraints. Okay. Okay. So those constraints have to be satisfied no matter what. Let's talk about the objective function. Okay. And so the objective function has 2 objectives. So on the one hand, we want to minimize the amount of deflection or the amount of deformation that this truss is experiencing. And we also want to minimize the cost of construction. Okay. And so the cost of construction, for this case, we're just going to take as a multiple of the total volume of the structure. Okay. And so the logic here is that the more material that you use to construct the truss, that's going to cost more because that's more material that you have to use. Okay. And so one thing you're going to have to do is you're going to have to compute the total volume of all the truss elements. Okay. And so to get the volume of a particular truss element, you're going to multiply its length multiplied by its cross-sectional area. Okay. And then from there, you're going to add to that a factor that scales with the Young's modulus squared. Okay. And the thought process behind this is that as the Young's modulus increases, that's basically saying that your material is getting stronger and stronger, right? So higher values of Young's modulus is stronger material. And so the stronger material that you use, it's going to cost more to manufacture and produce that material. Okay. And so our cost formula here has a term that scales with the Young's modulus as well. Okay. Okay. And so one example for your objective function here is something like the following. And so we're taking 2 things into account here. We're taking both the cost as well as the deformation into account. And so what you can do is you can take the square root of the cost divided by some reference cost squared plus the deformation divided by the reference deformation squared. Okay. And so I've written this one out for you just so you can have an example. And I've also given you an example code for the that completely solves the simple truss using Monte Carlo. And so I wanted to kind of give you an example of what that would look like. Okay. But for the larger truss, kind of a 25 bar truss, it's going to be up to you guys to actually write your own objective function. You can use one that's very similar to this. In fact, in my own solution, I do that. But if you can think of something better, something that kind of makes a bit more sense, you're free to do that as well. Okay. Okay. So that's the constraints and the objective of this optimization. Any questions on this so far? Okay. All right. Okay, so another constraint that we have here is that each of the variables here will have their own maximum and minimum values, and so this is just to kind of make sure that you don't pick anything kind of unreasonable for the length. We already have the other constraints, but each variable itself needs to have its own constraints, just so we keep everything kind of in balance. And so there's that as well. Okay. Okay, next we have the 3D truss, and so this is the one that's displayed at the beginning of the specifications. Okay, and so there are 10 design variables in this problem. So we have we have a couple Young's modulus, we have the cross-sectional area, and 6 length variables. Okay, and so where each of those length variables correspond to, you can see in this figure here, figure 4 in the specifications. Okay. And what I've basically done is I've split up this structure into the top part of the structure and the base of the structure. And so I'm basically letting you choose the Young's modulus for the top and the base, as well as the cross-sectional area for the top and the base separately as well. Okay. Okay, so the loads that are applied on the structure are given in this table, and so they're going to be applied. We have 4 loads here, so they're applied on these 6 nodes. Okay. And the X, Y, and Z components of those forces are given in this table. So, so you don't have to worry about changing this. And so this is kind of just for your own information. But we're for all intents and purposes, we're going to assume that the loads are fixed. Okay. Okay, and then when you apply those loads to the default configuration of the structure is going to deform in this way. Okay, so very similar to the last problem. The black is going to display kind of the original configuration of the structure, and in purple, that's the deformed configuration as a result of the loading. Okay. Okay. And for this problem, we have 6 constraints. And so the 6 constraints are the following. And so the total height of the structure has to be at least 200 inches. The total base area, which is the product of L1 times L2, has to be at least 25% greater than the middle, the area of the middle base, so L4 squared. Okay. The width of the top, L5, cannot exceed 75% of the middle base, so L4. Okay. The maximum force experienced by any truss element cannot exceed 350,000, and the maximum force experienced by the very top member cannot exceed 200,000. So the very top member of the truss here, this L5, this element between 1 and 2, that one has a stricter force requirements. The force there cannot exceed 200,000 pounds. Okay. And the last constraint that we have is that the height of the top section L6 cannot exceed the height of the base L. Okay. So these are all inequality constraints. So you're going to have to factor these into your code. Okay. Okay, so once again, our objective here is to minimize the amount of deflection as well as the cost of construction. And so your objective function is probably going to look very similar in this case than to the previous part. But again, I'll kind of leave that up to you in terms of how you can compute that. Okay. And I have a little bit more information here about, where each of the elements are and how to compute their volumes and how to compute their costs. Okay. Okay. And we have the parameter ranges for each of the 10 parameters. Okay. So a 10-dimensional optimization, that's a pretty sizable optimization, even by practical standards. So, this is definitely going to be a challenging problem to do. Okay. Okay. Any questions on the 25 bar truss? Okay, graduate problem. And so if you're taking this course for graduate credit, our policy states that you have to do an extra problem. And so basically the extra problem here is that I'm gonna let you create your own problem. And so I'm gonna let you kind of design kind of a base structure for a truss, and then you can optimize that design using your algorithms here. Okay. I may change this, and so it's only in this way right now just because I kind of ran out of time. But I may design another truss for you to do yourself. And so, but if you want to keep it this way too, if you want to design your own truss using the code, then we can do that as well. Okay. All right. And so for all the problems, you're going to compare the performance of your 2 implementations. And so remember, you're implementing 2 algorithms per problem. Okay. And so you're going to compare them in terms of the parameters that you obtained, the number of iterations that it required, and the time that it took to reach a converged solution. Okay. The next sentence is something that we're going to cover in a bit. We haven't really gotten to constrained optimization yet for nonlinear programming. But if you do something called a penalty method, you're still expected to satisfy all the constraints. Okay, so we'll talk about that in a couple of weeks. Okay. So that's kind of the requirements for the project. And so let's talk a little bit more about the kind of the nuts and bolts of how to use the functions here. Okay. So I've already written the code for you to compute an actual truss. Okay. And so the code for running a simulation on a truss has already been written for you. Okay. The only thing that you have to do is just use this code as if it were an objective function. Okay. And so if you recall kind of from the examples that we've gone over so far, we've used kind of an inline function or a MATLAB function to call our objective function. This is kind of the exact same thing that I've kind of already provided for you. Okay. Okay, so I've given you 2 functions here. And so one function is going to be called simple truss. Okay. And so the way to run it is like the following. And so you can do simple truss. Okay. Simple truss takes 4 arguments, or the first 4 arguments. These are basically all of the design variables for that problem. Okay. And so if you recall, for the simple truss, we have the total length of the structure, we have the height of the structure, we have the Young's modulus, as well as the cross-sectional area. Okay, so that's what those 4 things do. I have one additional argument here that's not a design variable, but that last argument there is going to be either true or false. And so that's whether you want to display the result or not. Okay. And by display, I mean basically the visualization of something like this. Okay. And so the reason I have that as an option, and so you would think that most of the time you would want to kind of see what the result is. The thing is that whenever MATLAB has to plot something, it really kind of slows the program down. So when you're first kind of running your optimization, when you're first kind of debugging and seeing how it works, I would definitely recommend you turn this to false, okay? Because the code is going to be evaluating the trust, many, many, many times. And so you don't want it to get bogged down, in trying to plot stuff when, you're going to be changing things around the code anyway, okay? I would only recommend turning that to true kind of once you're done or you're close to finishing and you kind of want to see the result of your optimal parameters, okay? Okay. And so the return values here are, there are two return values here. And so on the one hand, it's going to give you a vector called element forces. And so element forces is going to tell you the amount of force or the amount of stress that each truss bar is experiencing. And displacements is going to describe the XYZ displacement of each node in the structure, okay? And so you're going to use both of these results here in the constraints as well as in the objective function, okay? Okay. All right, and so for the bigger truss, it's going to be similar, and so the truss is the name of the function is called big truss, okay, and so as part of that, you're going to input all of the design variables here. So you can see we have 10 entries, one for each design variables, as well as a true and false thing, just like the previous one, whether you want to plot or not, okay. Okay, and then just like the previous function here, it's going to return the element forces. It's going to return the displacements. And then it's also going to return one more thing that's going to be useful for you when you're evaluating your objective function. So this code is actually going to compute the volumes of each of the truss elements as well. Okay, and then return that to you as a vector. Okay, and that's just mostly just to make it easier for you to compute the effect, because 25 truss bars is quite a lot. Okay. So I do have an example that I want to show you for that as well, and so we'll go over that in a bit. Okay. Any questions on this so far? Okay. Okay. Deliverables, and so let's talk about the things that you're going to have to turn in. And so in terms of that, I want you to submit all 4 of your codes. Okay, so that's going to be a big part of the final project, and you're also going to write a report as well. Okay. And so the report is going to have certain sections that we'll talk about in a bit. And these are all of the kind of the result tables that I want you to show. Okay. And so, it's a lot to go through. And it's going to seem like a lot, but, once you have your codes written, the codes themselves actually run pretty quickly. And so even though these trusses are fairly complicated, if you write your code well, even for a Monte Carlo code, it shouldn't take more than a couple minutes to run. And so, you should be able to produce all this data fairly quickly, okay? Okay, so the first table that I want you to show is just the optimal parameters, okay? In the 10-bar truss for both of your algorithms, okay? And so I want you to comment on the similarities and differences. And so, ideally, you would want both of your algorithms to obtain the same set of optimal parameters, okay? But that may not be the case. Your two algorithms may find different parameter sets, and that may be due to a variety of reasons. So maybe one of your algorithms kind of gets stuck in a local minimum, and it thinks that it's done there, and then that's the optimum that it reports. Whereas your other algorithm, maybe your other algorithm gets stuck in a different local minimum, and then it reports that one. Or maybe your other algorithm will be able to find a more optimal point. Okay. Because not all algorithms are going to perform the same. And I'll tell you for sure for this problem, there's going to be some algorithms that perform better than other ones, okay? And so I want you to comment on those differences, okay? It's not a requirement that both of your algorithms get the same result, but, I want you to be able to kind of explain why you think, these algorithms may be getting different optimal results, okay? Okay, and so table 2 here is going to be the same thing. And so I want you to show your optimal parameters, your optimal results for the 25-bar truss. Okay. Okay. Number 3 here is to compare your performance. Okay. And so by performance, I mean the number of iterations that it requires. And so some algorithms will require more function evaluation than the other. Okay. And I want you to comment on that. Okay. Okay. And so, results 1 through 3 here, those are going to be the main results. starting from result 4 here, I want you to kind of tinker with it a little bit and see if you can get that to change the results. Okay. Okay. Number 4 here is I want you to make a change in the objective function. Okay. So theoretically, if you change the objective function, it should also change your optimal parameters. Okay. Number 5, I want you to make a change to one of the constraints. Okay. And then observe kind of the results in the change of your optimal parameters. Okay. Number 6, I want you to use one of the pre-packaged optimization frameworks within MATLAB. Okay. And so MATLAB actually does have its own pre-packaged optimization algorithms. Okay. And so I want you to compare what you're getting from your codes compared to what MATLAB has found. Okay. So we'll cover the pre-packaged algorithms probably in the last week of the semester. Just because they're not that they're not that difficult to use. So step 6 here shouldn't take you too long. Okay. And then step 7 here, if you're taking this course for graduate credit, is to report the results of the graduate problem. Okay. Okay. So those are the main results that I want, and then I want you to organize it into a final report. Okay. And so the report here is pretty standard stuff, and so you're gonna have to write an introduction, a methodology section, a results section, and a conclusion. Okay. So your results section will essentially be kind of what we just covered. And then the introduction and methodology will be kind of an introduction to the course, an introduction to optimization, and then methodology. I always tell people that the methodology section is a really important section for scientific reports, because that's kind of the part where not only are you kind of explaining to your readers kind of how you obtained the result that you did, but you also kind of through the methodology you kind of demonstrate that you know what you're talking about. And so you can think of the methodology section as almost kind of like. You can almost think of it like you're almost teaching someone how to use these algorithms. Okay? So think of it as kind of an opportunity to teach. Okay. Okay. All right. So teams. So there are no teams, or at least the plan is for there to not be teams. Okay. So everyone's gonna have to write their own report and write their own code. Okay. But with that said, I do want you guys to work together on the codes, and so. Definitely feel free to discuss with your classmates, use the Discord server, work together on codes. If you're getting errors, you can check to make sure if you're getting the same optimal parameters. And so that's totally fine. So I want that. So I want you guys to feel like that, you don't have to work in solitude. So, because a lot of times, if you're running into an issue, odds are that someone else is running into the same issue, and having two brains kind of work on the same thing is always is always good. Okay. Of course, I'm gonna be available to help you guys with your code as well. So definitely feel free to come talk to me if you're having issues. But feel free to kind of talk with your classmates as well and get help from them. Okay. But I do want to be clear here. So working together on code does not mean that you have one person write the code and everyone else has pom-poms just cheering them on, right? And so I don't want you to just copy someone else's code. And if you do, it's very obvious. And so even if you make attempts to kind of change things, like change the variable names or change the arrangement, it's very easy for me to tell when someone's copied off someone's code. So you guys should be writing your own codes. And with optimization, you'd be surprised that there's kind of a lot of different ways that you can do this. And so write your own code, but debug things together. Just don't copy your own. Okay. Okay. And so this last section of the specifications here, I have kind of a step-by-step process on kind of how I suggest that you do this, because it's a lot. So there's a lot to do in this project. And so I think if you're just kind of looking at it as a whole, it can be kind of very overwhelming to kind of find out kind of what's the best way to start and where to go from here. Okay. And so what I have here is kind of a 9-step process in terms of how I think you should approach this project, and then just to kind of make sure that you're kind of making as steady progress as possible. Okay. Okay. So step 1 here is to look at the example code. So this is we're going to do this soon. So we're going to go over this in class in a bit. Okay. Steps 2 and 3 are to implement your first and second algorithms on your 10-bar truss. Okay. And to compare the results and performance with the example from step 1. Okay. Step 4 here is to familiarize yourself with the geometry of the 25-bar truss. Okay. Because with the 25-bar truss, there's a lot going on. So there's a lot of design variables, there's a lot of elements, there's a lot of nodes. And so it takes a little bit of time to, I think, familiarize yourself with, in terms of, which element goes where, which node goes where, what do each of the design variables represent. So, before you start coding stuff for the 25-bar truss, I definitely recommend, spend a bit of time, spend, 10, 15 minutes looking at the figure, kind of seeing where all the design variables are and what they all kind of correspond to, and it'll help in your code. I promise you that. Okay. Okay. Step 5 is to write out the equations that you're going to need to represent the constraints and the objective function. Okay, so I didn't give you those explicitly in the specifications here, and so you're going to have to come up with the mathematical forms for those on your own. Okay, most of those are going to be pretty simple, and in fact, you can take a lot of inspiration from the 10-bar example, but make sure that you write them out so you kind of know kind of what you're coding in. Okay. 6 and 7 is to implement your optimization algorithms. Okay, and so again, feel free to use a lot of the example codes that we're doing in class. In fact, for some of these, you can basically just kind of almost just drop the truss function in there, make some minor changes to the codes for the constraints, and then that's all it takes. Okay. Number 8, if you're a grad student, implement the graduate problem. Okay. 9. If you're at this point, all your code should be working, and so you should go ahead and run them to produce all the results that were outlined in section 4. Okay. And 10 is to write the report. Okay. Okay. And so before we go over the example, I've kind of been talking a lot at this point. I do want to say that, I mentioned this kind of at the beginning of the semester too, that, you guys are kind of my guinea pigs for this class. And so I've never taught this class before. I've spent a lot of time on developing this project and it's what I think is somewhat reasonable to do, at least in terms of what we're going to cover and how much time we have remaining. But at the same time, it's something that I'm paying close attention to as well, right? And because there have been a lot of times in my teaching career where I've given something there that I think is going to go one way, but then kind of goes a completely different way because of a variety of factors. And so, these specifications are kind of what I have planned, but, I'm going to be just very upfront with you guys that, if things don't go well and if things end up being more challenging than they are, I am open to kind of changing these requirements and making it more reasonable and more practical. Okay. Because the last thing that I want is, for you guys to have kind of a negative experience with optimization. And so, we have to have a certain standard. There are certain things that we have to do to kind of make sure that that you guys are getting a good educational experience in terms of taking things away from the class. But I don't want it to be overly burdensome that that you start to sacrifice your other courses or your health or your mental health, things like that. Okay. And so I'm watching this very carefully. And in fact, I'm going to rely on you guys a lot to kind of tell me how things are going in terms of writing the codes and running them and writing the reports and things like that. And I'm very open to making adjustments. So I wanted to be very open with you guys about that. Okay. Because on paper, when I was writing the codes, it seemed like it was really fun. It seemed like it seemed like a good thing. But then when I was actually putting it to paper here and actually writing the specifications, I was like, oh man, this is kind of a lot. I'm at 12 pages right now just for the instructions. And so, if things end up kind of more difficult than they seem, then, we'll definitely adjust. And so I don't want to, panic you guys if this kind of seems overwhelming at first. Okay. Okay. And of course, at any time, don't hesitate to reach out. And so, I'm here to help you guys, whether it be kind of a very simple kind of coding thing that you just can't get around, or maybe you're not getting the results that you want, or, you're having trouble understanding some algorithms. I'm here as a resource. And so definitely use me, as much as you can, email, office hours, make appointments, I'm here to help. Okay. Okay, any questions on any of this here before we start to go over the example? Okay, so let's go over. So this kind of took describing the final projects always takes longer than I thought, but that's okay. Okay, so let's go over the example code. And so what I've done, just to kind of get you started, I've implemented a Monte Carlo implementation for the simple truss. Okay. In fact, I actually need two of these things. So I need this and I need this one here. Okay. Let's go. Okay. Oh, so one thing I didn't mention in the specifications is that Monte Carlo is actually off limits. So Monte Carlo is the one algorithm you can't use for the final project, just because it's a little bit too simple. So I want you guys to use one of the other algorithms that we did. Okay. Okay. But this example is written in Monte Carlo, and so the purpose of this example is just to kind of show you kind of how I implemented the constraints, how I implemented the objective function. And I think more importantly, how to actually use the truss function, because it is a little bit strange. Okay. Okay. And so, hopefully you guys remember kind of the Monte Carlo code that we went over in class, because this is kind of a direct application of that. Okay. All right. And so for this Monte Carlo, implementation, I've set the number of samples to take to be roughly 1 million. Okay. And I've set the basically just kind of dummy variables for all these things. Okay. And so I've set my convergence threshold, which I don't think we actually use here. And so I basically run, all 1 million simulations. Okay. And then we jump into the loop here. Okay. Okay. So remember, one big thing about Monte Carlo is that you have to sample all of the parameters. And so you can see here that I'm sampling the values for L, for H, for the Young's modulus, and the cross-sectional area. Okay. And so these formulas here are based on kind of their upper and lower bounds, as we discussed in the specs. Okay. And then this line of code right here actually runs the simulation. Okay. And so notice here I'm using the simple truss function, and I'm plugging in all the parameters that we just randomly sampled. We put in L, H, E, and A. Okay. And notice how the last argument here I've set to false, because I don't want it to plot just yet. And so I don't want it to plot until the end. Okay. And the two things that we're returning here are the elemental forces as well as the displacements. Okay. Okay. All right. So the next thing that we're going to do is we're going to check and see whether the constraints were violated. Okay. So we have 3 constraints in this problem, and so we have to first compute the total length. Okay. And so remember what we said is that the total length has to be at least 500 inches. And so we compute the total length, which is 2 times the length L. Okay. And so if that total length is less than 500, and so basically what we're checking for C here is like if this constraint is violated. Okay. What I do here is that we reject this point, and so I have a kind of a separate variable here to track how many design points we've rejected. Okay. And you can see here that I'm using this kind of key word in MATLAB called continue. And so what continue does is that it skips the rest of the body of the loop, and so it doesn't run any of this other code, and it just returns back to the start of the loop here. Okay, and so if we continue, then what we're going to do is we're going to resample different values for each of the design variables. Okay, and then we're going to check the constraint again. Okay, and so for this constraint, this one's fairly simple. We're just checking the total length. Okay, next thing we're going to do is we're going to check the ratio of the height to the length. And so we're going to take H divided by total length. And so if that H to L ratio is less than 0.2, or in other words, if we've violated this constraint, then we reject it and we move on to the next design point. Right. And so the next thing that we're going to check here is the maximum force. Okay. And so for this, we're going to use the E force vector that came out of the truss function. Okay. And so I want to compute the maximum elemental force. Okay, so to do that, I'm using 2 MATLAB functions here. And so first one I'm using is abs. Okay, and so what abs is going to do is that it's going to compute the absolute value of every entry in the vector. Okay? Because the way the truss code works is that it could return to you negative forces. And so the negative forces correspond to a compressive load. So we want to make sure we compute the absolute value just to make sure everything's positive. And then we're using this max function here to compute the maximum value of that force. Okay, and save that in here. Okay. And so if this maximum elemental force, if that exceeds 350,000, okay, then again we're going to reject this design point and we're going to continue on to the next problem. Okay. Okay. All right, and so if we reach this point in the code, so we checked all 3 of our constraints. If we reach this point, then we basically have a design point that satisfies the constraint. Okay? And so here we can actually compute the objective function. Okay? And so remember, our objective function has 2 components. And so on the one hand, we have the cost, And so the cost of the truss structure is going to be the total volume, um, plus the term with the Young's modulus. And so you can see this code here computes the total volume of the structure. So we're computing the volume of all the horizontal elements. We're computing the volume of all the vertical elements. And here we have the slanted elements as well. Okay. And then to get the total cost, we're adding together the total volume multiplied by that factor, which is the Young's modulus squared. So 2 times e to the minus 8 times e times t. Okay. Okay, and then from there we're computing the maximum deformation, and so this is going to use the displacements vector that comes out of the truss structure, okay, or the truss code. Okay. We're computing the max, and we're computing the norm. So this vec norm function here is going to compute the magnitude. Okay, just to make sure we're computing all the same things. And then from there we're going to compute the objective function. So the objective function here is square root. The total cost divided by 5,000 squared plus d max divided by 2 squared. Okay. And then here we're checking to see if this is better than our previous point. And so if this f test is less than f best, okay, then we save all of the design variables and we print it out. Okay. Okay. And so at the end here, you can see here, we're going to run it one last time with the best variables. And in fact, for this final run, we're going to set this to true, and that's going to plot the results. Okay. And I have a final print statement here, which tells you, how long the whole simulation took with the amount of rejections that took place. Okay, so let me go ahead and run the code here. So actually, I think it's going to take maybe a couple minutes. Okay. And so you can see here that I'm having the code print out a statement every time a new optimum is found. Okay, and this one's gonna take a little bit of time because it is Monte Carlo, so it's quite slow. So it's gonna take a couple minutes, but I'll go ahead and let that run, and if you guys have any questions, we can kind of discuss it now. And so even though you can't use Monte Carlo, you can't, or I should say, you can't turn in Monte Carlo as one of your algorithms for the assignment. You can still write the code. And so Monte Carlo is actually really good for testing in cases like this. And so you can definitely, for the 25 bar truss, feel free to implement a Monte Carlo solution and kind of see how that stacks up. Okay. Okay, and so you can see as the algorithm kind of gets further and further, it's being less successful in finding new parts or finding new optimums. Because this one right here has apparently been pretty good. Okay. And you can see sometimes it's only just a minuscule improvement. And so the objective function went from 15.19 to 15.186, and so very small. So that's how what that tells me is that this is probably pretty close to the optimum at this point, because it's getting really hard to actually improve it in any given way. Okay. Right, almost done. 90% there. Okay. Oops. Error. It's not good. Too many output arguments. Oh, whoops. Oh, that's disappointing. So there's a typo in the example. I'll fix that in a bit. I had another version of this code where I computed the reaction forces for the truss, and I had that be part of the objective as well. But I figured there was kind of too much going on, so I took it out. So I'll fix that. But you can see here that's basically kind of an example of how it runs. Okay. Okay, so definitely use this example code. It's definitely going to be useful for you in terms of developing your own codes, and very useful for the project in general. Okay. Okay, so that's the project, and so it's going to be due in about a month and a half, and so you have quite a bit of time. But just kind of keep in mind that these next few weeks are probably going to be the most busy in the semester. So make sure you're kind of getting started. And to kind of help with this, so homework 5 is going to be the last kind of major homework assignment. After homework 5, I don't plan on assigning any more homeworks. just to kind of give you just kind of give everyone time to work on the project. Okay? I will give out kind of an optional kind of practice because we are going to be going over more algorithms, especially after Thanksgiving. So I'll give kind of some extra practice problems if you want to get some practice on doing constrained optimizations, but it's not going to be turned in for credit. Okay, so you can kind of focus mostly on the project. All right, any final questions on the project before we move on? Okay, all right, so that's out there. So definitely go check it out. All right. Okay. All right. And so let's get back to where we were. So that took a lot longer than I thought. It always takes longer than I thought to explain projects. So I don't think we'll finish pattern search today, but I did want to finish coordinate search, and we'll kind of start to talk about the idea of pattern search. Just so that you can kind of get started on it for the homework. Okay. So for coordinate search, let's actually come back up here to kind of remind ourselves what that is. Okay. So coordinate search, or the idea behind the coordinate search algorithm, is to kind of make an improvement over random walk. Okay. So random walk, its intentions are good, and so it was developed with kind of good intentions, in terms of what it was hoping to achieve. But in practice, random walk is a little bit too it's a little bit too random, and in fact, a lot of times it can kind of get stuck in a lot of places, as kind of a lot of people are experiencing as you're starting to work on the homework. Okay, and so the idea behind coordinate search is to kind of take some of the randomness out of it and to make it a kind of a more systematic process to find optimum from there. Okay. And so the idea behind random walk is that, or the idea behind coordinate search is that instead of walking in a random direction from any given point, we're only going to be walking in the coordinate directions. Okay? And so we're only going to be changing one design variable at a time. Okay. And so the direction now kind of becomes not really much of a, it's more trivial in this case because we know exactly which directions we're going to walk in. The challenge with coordinate search is actually going to be to compute the step length. Okay. And so for any given coordinate direction, okay, we have to determine, how big of a step that we want to make in that direction. Okay. And the idea here is to make that step in such a way that leads to the biggest improvement of the objective function. Okay. Okay. And so kind of what we kind of were ending, what we kind of finished discussing was that, one way to determine that step length is to use kind of the classical method. And so, we kind of end up putting an optimization problem inside your optimization problem because you're solving a 1D optimization to find the optimal step length for a multi-dimensional optimization problem. Okay. And so that's exactly what we're doing here. And so this is the example that we kind of ended up with. And so for this example, we're working with this objective function here. Okay. So we have x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay. And so if we're making only one step in each direction, right? And so let's say that we're only stepping in the x1 direction, we can mathematically represent that by saying f of x1 plus lambda, okay, where lambda is the step. And so if we plug that into our objective function, basically everywhere we see x1, we're going to plug in x1 plus lambda, okay? And then we take the derivative of this expression with respect to lambda, set it equal to 0, then we can solve for the optimal length. Okay? And so that's what we did for both the x1 direction. And so this formula here is the optimal step length in the x1 direction. Okay? And this formula here is the optimal step length in the x2 direction. Okay. And so the idea is that if we step in the x1 direction and we use this formula here to determine the step length, that's going to be the best that we can do. And then the same for the x2 direction here. Okay. Okay. So that was just kind of a recap from last time. So hopefully you guys have those equations in your notes, because let's go ahead and look at the code in terms of how this is implemented. Sorry, iPad, you were on the sidelines for the majority of class today, and then you were back for 2 minutes, and then you're gone again. Okay. Okay, so this is the example code for coordinate search, and so you can find this on the Canvas site. Okay. By the way, coordinate search a great option for your final project. Okay. The only thing that you have to take into account is you have to implement the constraints in here in some way. Okay? Because right now we're kind of assuming purely unconstrained optimization. Okay. All right. So the first part of this algorithm here, you can see we're defining the number of iterations. We're defining the initial point, the initial objective function value. So all of this is pretty standard. Okay. Let's jump into the iteration loop, because this is kind of where things start to get interesting. Okay. Okay, and so in classical kind of coordinate search, you know, we're only changing one variable at a time. Okay, and so that's what we're doing here. And so what we're doing in this part of the code here, okay, is that we're only changing x1, right? And so first thing we're doing is we're computing the step length. Okay, so we're calling the step length 1, and so we're plugging in this formula here. Okay, so that's the formula that I just highlighted in the notes. Okay. And then once you compute that step length, you can apply that to x1 in this way. Okay. Okay. And so that's basically it, right? And so you compute the step length, and then you change that design variable according to that step length. Okay. So you just basically add that step length to the variable value. Okay. Okay. But of course, you know, the thing that I'm kind of skipping here, or the thing I'm kind of glossing over, is this if statement here. Okay. And so this if statement is basically an opportunity for us to end the algorithm early. Okay. And so the way that we're determining that is that if the step length that we compute here is something that's really, really small, in other words, it's close to 0, okay, basically what that's telling us is that if we step in this direction, there's no step that we can take that will actually improve our solution. So, you know, we're basically at the optimum point if our step length is close to 0, okay? And so we can write that into an if statement. So if the absolute value of that step length, okay, so in other words, we're making sure that it's positive, is less than the convergence threshold, which is kind of what we defined up here, okay, then we can kind of break out of this loop. So we can say that the algorithm has converged, and we use this keyword break. Okay, so the break is going to break out of the for loop and bring us to the end. Okay. Okay. So that's the change in the x1 direction. Okay. And the x2 direction, we're going to change it, you know, in this way. Okay. So we're going to plug in the formula for the second step length. This is going to be 2. Once again, we're going to check for convergence. We're going to check and see if this is less than a certain value. Okay. And then we're going to apply that change to the second design variable. Okay. And so we just keep doing this until we reach convergence. And so, you know, and so notice how, you know, we're going to iterate at the maximum of 500 times. And so in the worst case, we're going to iterate 500 times. But let's see if we can achieve convergence faster than that. Okay, so let me go ahead and run the code. Okay. And so if I run the code, you can see that our algorithm here has converged in 24 steps. Okay. And so it only took 24 iterations for this optimization algorithm to converge, which is much less than the 500. Okay. So if you compare this, you know, to like a Monte Carlo, simulation, Monte Carlo, you also have to run things in the hundreds of thousands and the millions. So 24 steps is a lot faster than, you know, than Monte Carlo would be in this case. Okay. Okay. So that's coordinate search in a nutshell. So coordinate search, you know, kind of the key points here is that you're changing one variable at a time. And kind of the most difficult thing is determining, you know, what the step length should be in each direction. Okay. Any questions on this? Okay. All right, so that's coordinate search. Let's come back to the iPad. Okay. So let's go over, let's start talking about patterns. Okay. Okay. So pattern search is the fourth algorithm that we're going to go over. Okay. So there's lots of variations on pattern search. So pattern search is a very kind of reliable algorithm, and a lot of people have kind of came up with their own improvements to pattern search. Okay. And so it was actually kind of difficult for me to kind of get a kind of a very basic vanilla pattern search, which is kind of what I have here. Because in reality, there's a lot of kind of spin-offs and a lot of improvements to this. Okay. In fact, that process of taking an existing algorithm and kind of adding a twist to it to improve it is actually a pretty common thing in the field. So and actually pattern search was developed in that same way. So pattern search, the way it was developed, it was developed as a way to improve coordinate search. Okay? And then coordinate search was developed as a way to improve random walk. So we're kind of going along the progression of history, kind of almost think of it like that. Okay. Okay, and so the basic idea of pattern search is this. And so, in coordinate search, right? Coordinate search has a lot of very nice properties, right? And on the one hand, it makes a lot of intuitive sense to kind of just change one design variable at a time. Okay. In fact, if you were to ask someone to optimize something manually, they'd probably opt for an approach like coordinate search, just because it's kind of easy to kind of keep track of things when you're changing one thing at a time. Okay. But if you were to change things one at a time, I don't know what did I do? Okay. Okay. But the issue with coordinate search is that it may not be efficient to always stick to those directions, right? And so kind of the weakness of coordinate search is that you're fixed to certain directions that you're searching in, and that may not be the most efficient path to finding the optimum. Okay? Because remember, kind of the thing that sets apart a lot of algorithms is not the ability to find an optimum. And so lots of different algorithms can find the optimum of an objective function eventually, right? That's why Monte Carlo exists. And so, all these new algorithms here, finding the right answer is not the objective. Well, I should say it's a requirement, but it's a requirement that's easily met. And so kind of the objective of all these algorithms is to be faster than the previous one, right? And so your algorithm is rated or kind of judged based on how efficient you can be. Okay. And so even though coordinate search works well in a lot of cases, it may not be as fast. Okay. And I think kind of a visual illustration for this kind of is really nice. Okay. So once again, I'm going to draw my 2D plane here with the x1 and x2 axes. Okay. And once again, let's say that we have an optimum point here. So that's where we want to go, right? And we want to design an algorithm that takes the shortest path to that optimum, okay? Of course, beforehand, we don't know what that optimum is, right? If we did, then there'd be no point in running the algorithm, okay? So we want to find an algorithm that can both find where that optimum is and get there as soon as possible, okay? Okay, let me kind of illustrate to you what coordinate search looks like, okay? And so if we start from a point from down here, okay? Ideally, the best thing that we would do is we just make a beeline to the optimum, right? And so we take steps, we go like that, right? That would be the best thing to do. So we would reach the optimum in one step, okay? That's impossible in most cases, but it would be nice, right? Okay. The weakness of coordinate search is that it's literally impossible to move on this trajectory, right? Because we're limited to the coordinate directions. Okay. And so if we were to do coordinate search, we would do something like this. And so we'd move in the horizontal direction, then we move in the vertical direction, then we move in the horizontal direction, and then in the vertical direction, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical. Okay. And so our path there kind of ends up being this kind of zigzaggy looking path. Okay. And so we get there, right? And so we arrive at the optimum solution eventually. It's just not that efficient because we have to kind of make a lot of turns and a lot of kind of small steps and things like that. Okay. It would be really great that if we could, find the pattern or kind of find that direction or at least get an estimate of that direction that's going to point us to that optimum, then we can actually use that to make our steps more efficient. Okay. Okay. So like I indicated earlier, right? It would be great if we can take a more kind of direct path to that optimum. Okay. But of course, we don't know what that direct path looks like a priori, right? But let's do this. And so I'm going to go ahead and erase a lot of these later steps. Okay. So let's say that we start with a coordinate search, right? So we take two steps, right? So we take one step in the horizontal direction, one step in the vertical direction. Okay. What if we connect these two, right? And so what if we actually kind of visualize this as a vector, okay? And then draw a vector from the starting point to where it would be, right? And so if we were to combine those two steps into one and make kind of one step to that location, that's what this would look like. Okay. So this orange vector right here, this is the two. Okay. That orange vector is the result of the two coordinate steps, right? So visually it's basically just the sum of those two vectors. Okay. What if we were to extrapolate this? And so, after making two coordinate steps, what if we take this direction here? What if we take this orange vector and apply it right there? Okay. Okay. And so after making the two coordinate steps, we would get a certain direction, right? Based on how long we stepped in each of those coordinate directions. Okay? And then we arrived at kind of an oblique vector that looks like that. Okay. This vector right here, okay, that we obtained from our two coordinate steps, two in this case, so we have two variables. This is what we call the pattern direction. Okay. And ideally, the pattern direction is a more direct path to the optimum. Okay. And so instead of taking two steps per iteration, where we take, in coordinate search, we take a step in each of the coordinate directions. What if we take a third step, where that third step is defined by the pattern direction? So taking a step in this direction would be good, because let's say that we're able to kind of take a relatively large step from there, okay, and then once again we do another two coordinate searches, okay, just to make sure that the pattern direction is fine, okay. We get another pattern from these two, okay? And we make another pattern jump. Okay. Then we have another 2 steps. And make a pattern jump like that. Okay. So this right here is a much more efficient path to the optimum, and because we took advantage of this pattern direction as opposed to kind of limiting ourselves to the coordinate directions. Okay. Okay. In fact, we can write a formula for the pattern direction. Okay. And so the pattern direction will be given by some vector pi. Okay. And the way we compute that, we take our current design point xi minus xi minus n. So this xi right here, this is the current design vector after one full cycle of coordinate search. Okay, so after we basically search in each coordinate direction. And it's xi minus n here. This is the design vector before performing that coordinate search. Okay. Okay. So it's literally just vector out, right? And so you're subtracting 2 vectors and you're getting kind of the pattern direction from there. Okay. Okay. And then once you have the pattern direction, you can take kind of one extra step in that direction, to make your algorithm more efficient. Okay. And so after we do our coordinate search, and so for a 2D problem, this is after we take our 2 coordinate directions, we can have xi plus 1 is equal to xi plus alpha pi. Where pi, that's our pattern direction, xi is our design vector, okay? And this alpha here is the step length in the pattern direction. And we'll talk a little bit about computing that step length because it's a little more complicated in this case. Okay. Okay. And so with this kind of change or this kind of improvement to coordinate search, ideally you should be able to reach your optimum much more quickly than before. Okay. All right. Any questions on this? Okay. All right. And so the next thing we're going to talk about, and this probably take us to the end of class, is how do we determine that step length? Okay. So in our previous coordinate search, we basically used classical methods, and so we took derivatives and we set it equals 0, and we use that to find the optimal step length, right? So that's perfectly valid for cases that you can use that for. Okay. But I did mention back then that it was kind of cheating a little bit because we're using classical methods in a nonlinear programming scheme where most times you're not going to be able to do that. Okay. And so the challenge that we're going to have here is how do we determine that step length? Both for a coordinate search and for the pattern step here. Okay. How do we determine that without taking derivatives? Okay. 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 And so the answer to this conundrum is actually to rely on one of our 1D methods. And the 1D method we're going to use might surprise you a little bit. It'll be it's actually the very first one that we went over, which was the elimination methods. Okay. And so it's not exactly that, but it's very similar. Okay. All right. So because the basic idea is that kind of once we reach the step, once we've kind of determined the pattern direction, we want to take the biggest step in this direction that will lead to the biggest improvement of the objective function. Okay? But we don't know exactly how big that step is going to be, and we actually don't even know what direction we should step into, right? Because that step length, even though I'm calling it a length, you could very easily step in the negative direction and the positive direction. Okay. And so there's actually kind of two things we need to determine first, right? So which direction we should step in, and what the magnitude of that step has to be. Okay. Okay. And so each one is kind of tackled individually, although kind of the way of doing so, they're kind of connected. Okay. So let's talk about the direction of the step first. Okay. And so the way we're going to determine the direction of the step is actually quite naive, at least logically speaking, right? And so we're going to do like a test step in each direction. So we're going to test step in the positive direction and test step in the negative direction. Okay. So positive step would be something like this. We have fxi plus positive alpha pi versus f of xi minus alpha pi. Okay. And then all we're going to do is we're going to see which one actually leads to a bigger improvement, right? In a lot of cases, you know, one of these is actually going to lead to it's going to lead to the objective function getting worse, okay? And so you know, you just have to kind of pick one to see, you know, which one is best. Okay? And so if you have a case where you take a step, okay, and I'll say this too, that usually you're going to start with the default value for alpha. Okay, so you can actually evaluate both of these. Okay, and so that's usually a parameter that you're going to set within the algorithm itself as well. Okay. And so you're going to test both of these, and if one of them leads to improvement, that's great. And so if one of them leads to improvement, then you're done. Then you kind of just go with that. Okay. Where you kind of get into a pickle where like maybe you test both of these and neither of them lead to an improvement. Okay. And so in those cases, then we're going to start to modulate the alpha. You know, in other words, we're going to reduce its value until we actually do see an improvement. Okay. But I think we'll cover that next time because that's it's a little bit more logic to get. But we're just about done here. And so after we talk about that, then we'll do the example, and then after that we'll go over the last algorithm in this section, which is the Nelder-Mead optimization algorithm. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. So definitely take a look at the project. And so even though we spent 45 minutes talking about it, there were some details that I didn't fully go over. So make sure you kind of read that document very carefully. And go ahead and get started on homework 5 as well, because it's depending on how you feel about coding, it can definitely take a while. Okay. All right. So thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you guys next week. Online, that on campus. Yep. Exactly. That's exactly what I want you to do. Yeah. And then for 2C, when we have to do the combine the two methods. So we're running Markov, determine what the best values are from that, and then taking those and then throwing them into the next one. Exactly. Yeah. So that one as well, you can copy, but that one you'd have to just kind of copy and paste the codes from example 1, example 2. Basically just one on top of the other. Okay, no, that's how many? So it was 30 to rewrite it. Oh yeah, that works too. Yeah. In fact, that's good because then you'll get more practice. That's kind of taking what's already there, but just rewriting it out. Perfect. Then I wanted to check in. I'm getting through homework 5. Yeah. It's kind of I wanted to see if you think about this correctly. So I'm in part B. This one random walk. I inputted all the settings to the function. I know it's supposed to be random and it's showing up. So you said it's supposed to be around this value. I'm getting the values. Yeah, first value. It's supposed to be that. So that's a typo. Okay. So what I did, all of these settings are the same here, but I was playing around with this one a lot. This one was giving me a lot of issues. And so what I did, I forgot I changed. So near the bottom to it, I actually changed this code right there. And so instead of having it be divided by 2, I have that I had multiply 0.9 instead. Okay. So the step one didn't go down. Okay. But then if you do divide by 2, you should get it. So this should be this should be like this. Okay. Yeah, because we didn't really discuss this. For like for future purposes, like I was going to have this project. Just what was it you said? 0 point. So that's kind of a level that you can turn. And so the divide by 2 is actually kind of arbitrary. So if you think about it, each time that's really impressive. It is. And so if you multiply by 0.9, then the step length is not going to reduce nearly as quickly. So then you're going to be randomly walking. And so that's why for my answer, we end up with a much smaller value for the objective value, because it's iterating, it's just taking way more steps.
Okay. But I did notice too, like if I increase the iterations, I do have
Yeah.
which is,
Yeah.
like, doesn't that just mean I'm looking for more directions?
Yes, yeah,
How come?
it's just taking more steps. And so whether you, because this algorithm stops when this step point reaches the main step. And so you can either slow that down by instead of dividing by 2, or you can just increase this to make kind of force it to take more steps for
Right.
So they both kind of end up with the same effect.
Was the value that size of 500 not the optimum then, because it was finding?
So actually what I think this problem is that it's pretty unbounded.
Yeah.
And so I think the true optimum is going to be at minus infinity. So,
Okay.
and so basically it's trying to walk to infinity.
That's what I was wondering too, because it was, because it's multi-variable basically.
Yeah.
You know, I was like, oh, maybe like I said, I'm not, but
Yeah.
I just wanted to check in.
Yeah, that's what, I haven't done a thorough analysis of this function, but it seems like it's unbounded. Because, you know, it shouldn't be having that behavior. So if you increase the steps, it shouldn't just keep getting higher and higher and higher. So it only does that if the problem's unbalanced.
Okay.
I'm glad I was on that one when I did my initial guesses.
Yeah.
I didn't change one. I left them all at 0, and looking at the results, and this doesn't make sense. Because I changed the boundary condition.
Yeah.
Oh, and, we did it. That was good. After we did it. And then when I did it, it ran perfectly on.
It's always small things like that.
But that was working on it yesterday and not telling well, so.
Blame it on the sickness.
I think I am.
Yeah.
All right. Have a good weekend.
Thanks, you too.
I'm sorry.
Get some rest.
That's what I've been doing.